First, I want to welcome you all to Maya HTT's webinar for efficient random and sine vibration analysis. My name is John Hsu. I'm the Simulation Services Director for Maya HTT. I'll be doing the presentation for you here today. First, I just want to start with why should you pay attention instead of using this time to answer emails? Well, your boss thinks you're busy. I just want to say that what you can hopefully get out of this is a more accurate results for your random and sine vibe and significantly faster results. So if you're just thinking about getting started in random and sine, I'll provide a quick summary of why it's important, show how efficient it can be. If you're already performing this type of analysis, in the next 30 minutes, I'll show you how our structural analysis toolkit can make your random and sine vibe 200 times faster. And if you're already using the structural analysis toolkit, we can make sure you've got the latest version, that you're using the latest processors and getting the most out of it. A little bit of an introduction for Maya. We are a software-driven engineering solutions company. We're a #1 partner with Siemens Digital Industries. We started in space. That's our background. That's what we do, but we've expanded into almost every type of industry there is and supported everyone from tomatoes to automotive to cars, aero, space, everything. We have about 75% of our staff are scientists and engineers, and that's out of 225 people. We actually authored 30+ modules for Siemens. So we do a lot of the developing ourselves, and a lot of the modules that are integrated into the Siemens products, in addition to software like this that we'll talk about today that we do on our own. At Maya, we have 3 main groups that work together to really help you get the most out of your work. We have an engineering software development group, so where we actually develop software like the structural analysis toolkit, like the modules that we build for Siemens. We have a digital solution distributor, so we'll make sure we get the right licenses, the right software to do your work. We also have a consulting and integration group. So my group, actually the simulation services, is part of that, where we do structural analysis, thermal analysis, CFD analysis as well. We do PLM integration. We have AI and IoT group. And you can see on the right side there, all the different areas that we work in. Now, first, I want to start out with a question here for you and ask what your experience level is with sine and random vibration. So you should see a poll up on the screen there. And if you want to answer there, we'll show the results here. Just want to get a feel for the experience level of the group and how familiar you are with that. We're getting answers coming in. It's actually about even across the board so far. I'll show you the results here at the end. Give it another few seconds. Oh, we have doing the analysis pulling ahead here. All right, I'll go ahead and close that poll and we'll share the results here. So we have a majority of you have done random vibe and sine vibe analysis before. It's as to be expected. Some of you familiar with it, maybe looking to get into it, and some of you not familiar with it at all. So I'll try and cover topics for everyone and make this applicable to all of you here today. So quick agenda. Like I said, I'll briefly cover why do we care about vibration. Then I'll give an intro to our structural analysis toolkit, and then go into more detail about the structural analysis toolkit processors, what they do, a little bit of the theory behind them, and then provide a quick demo as well. So why do we care about vibration? Well, let's start with where vibrations come from and where they might apply in our engineering design process. So they come from all, any external sources. If you have a car riding on a rough road, anything driving along a surface, there's going to be vibrations. A plane, you have the aero loading causing vibrations. You have the engine inside causing vibrations. And then for the space industry, most of the vibrations are going to be coming from a launch. So you've got the vibrations of the engines, you've got the noise of the engines causing vibrations, and all those give you some sort of time history of accelerations that you can look at. But then what do we do with that once we have that? So you've probably seen some variation of this is a really stripped down V&V diagram. But if we look at the engineering development process, it's generally going to start with requirements. And I'll do sort of a space-based example here, but this applies to many industries. If you have a spacecraft sitting inside a fairing, like I mentioned before, you're going to get a lot of vibrations from the transmitted into the base of the spacecraft where it connects. And additionally, you will get many vibrations due to acoustics that are reverberating off of the panels and hitting these big panels on the satellite, on the spacecraft itself. And that's causing vibrations, random vibrations, to shake all the components sitting on those panels. Oftentimes you'll get specs that come from launch guides. They'll give you the acoustic specs, they'll give you a sine vibe, and then a random vibe spec as well. And you can see here, a lot of times low frequencies are driven by your steady state accelerations, your sine vibe. That's why often in sine vibe, we only test to about 100 hertz in space industry. Aeroacoustics are driving a lot of your mid frequencies, and then structure-borne vibration for the higher frequencies. So you've got your requirements there. Next, what you're going to do is do the design and analysis for your spacecraft, your subassemblies, your components. You're going to take those specs that you have, and you're going to apply them to your models that you build. Now, what we're talking about today is base-driven sine and random vibration. And what that means is the analysis and the testing is done on a fixed base. So if you've ever seen a shaker table, that's what we're talking about. It's the article is fixed to that table and shaking. In your analysis, you pick a single point that, you just grab the bottom of this adapter here and fix it to a single point, and that's where you're putting in this input and driving the analysis, and then getting your results. And then once you get your results on the back end, you're going to do testing. And so you're going to take the same inputs that you analyze to, you're going to do component testing, and then even often do full spacecraft testing. In this application, you're often doing a sine sweep to 100 hertz. So we kind of have an idea of where that fits in with the process, but then how does something like the structural analysis toolkit or being able to do random vibration faster fit? Well, if you've seen some curves like this, the cost committed, cost of change, the important thing to remember is anytime you can move farther to the left on these curves, you're generally going to get reduced time and cost for your product development, and you're going to improve your quality and your durability. So if you can do random vibration, sine vibe faster, you can do more iterations, you can do it more frequently, and you can do it more accurately, you're really going to improve your product and your time schedules and your costs. So let's do an intro here to Maya HTT's Structural Analysis Toolkit. Let's talk about what this is. So it's a fast and accurate, random and sine base-driven solution for Nastran normal modes. So that's taking the Nastran solution 103 modes, doing random and sine on top of that. It accounts for non-Gaussian probability distributions. Many types of random software solvers, they only assume zero mean Gaussian. We'll talk about that a little more later. SATK, if I say SATK, Structural Analysis Toolkit, SA Toolkit, it's all kind of our brand names that we call that. So this also computes peak composite failure metrics. so you can actually get the random results for your composites. It'll account for modal truncation, ResVec, if you're familiar with Nastran. It can compute margins of safety, can process large files. You don't have to read them in. You can just process them through our toolkit of greater than 1 terabyte. And it's a product that we've been continually investing R&D in since 1998 with proven spacecraft and other industry heritage from many different customers. Again, what this includes, so to go into a little more, it takes SimCenter and MSC Nastran data. So it's directly manipulating the OP2, that's the results file. It'll work for Windows and Linux. We can read the results into FEMAP or SimCenter 3D. It can run in batch, and it'll produce some automated reports for you as well that you might find useful. Now, I said it's fast, and I'll hit on this a few times because it's an important point, but it's very fast. If you look here, we have a sample model, just a demo we put together. It's got about 160,000 nodes, 130,000 elements. There's a mix of laminates and 1D, 2D, 3D, did 34 modes. The results file for the modes is about 1.5 gigabytes, just to give you an idea of the size. So if you look at your, your common FEA solvers, Nastran, Abacus, Ansys, it'll take more than 30 minutes to get the RMS stresses with a random vibe solve. So SATK, it actually can solve that in 8 seconds and give you all those same stresses. So it's over 200 times faster than a lot of the other major FEA solvers. And if I can make one point in here, I want you to think about what that could do for your workflow. If you could solve something over 200 times faster, if you're doing a lot of random, or even if you're not doing a lot, now you could do it a lot. You could do those iteration design cycles quicker. You don't have to make sub-assemblies. You don't have to spend a lot of time reducing your model because you can just use the same model you were using for stress because it's going to solve fast. So just think about what that can do for your workflow. Now it includes a whole processor suite. I'm going to talk a lot about random. That's the key thing. That's what really makes this an intriguing piece of software because it does it so fast. But it does SignVibe. It has modal summary and energy processor, stress processor. It can process grid point forces and joints, so you can use that to pull out forces for, say, bolts or welds, element forces, mass summary. But the key is really going to be that random and SignVibe processor. I'll go ahead and launch another question here before we go in and just ask, what are your biggest pain points when setting up, running, and post-processing random and SignVibe analysis? And you should see that pull up now. If you want to provide answers, see answers coming in. Getting there a bit. Hopefully I was able to hit on the things that were important to people in the answers. And it's looking like a lot of people, the developing an accurate but coarse enough mesh is coming out about for 50%. We'll close the poll here shortly. Yeah, okay, we'll go ahead and close that. I'll share the results. So it looks like, yeah, model prep, meshing, getting that right. I mean, that's no surprise. That's what all these tools really are for. A lot of this is to make that initial meshing better. And for the random, because it takes so long, you have to spend a lot of time really trying to coarsen up your model, but make sure it's still accurate. Looks like we've got also solving slow and can't easily get all the results you want as well, along with a few for confusing setup and never done it before, don't know why. So let's go ahead, we'll talk about this, and hopefully I can show you how SA Toolkit can really help solve some of those problems for you. Let's talk through this. I'll just hit these real briefly. The modal processor, It's in there and provides some useful insights to help understand your model better. You might have scripts and stuff that do this already, and that's fine. These we include just to help you investigate your model a little easier. This is the energy processor. You can, some of the output you get from that, you can do modal strain and kinetic energies, and also do it by groups. So you can really see which groups are active in which modes, which can be helpful if you're trying to debug your model. Now the sine vibe processor, I apologize, these next two slides might be a bit wordy, but I just wanted to hit the main points. So the sine processor is efficient and accurate, again, base-driven harmonic vibration. It analytically determines phase-consistent von Mises stresses. It's parallelized and it can run in batch. It's part of what makes it fast. And it can, again, gives accurate results with the Nastran eigenvectors. And the key point at the bottom here is for all the general results that something like Nastran solution 111 can create, acceleration stress tensors, SA Toolkit gives the same exact results. Now we're going to talk a lot more about the random processor because I think that's what everybody's going to be more interested in. It's an efficient and accurate, again, base-driven random vibe simulation. We use some state-of-the-art integration schemes. I won't get into the details much of that, but that's what makes it so much faster than the competition. There's no need to specify integration frequencies. The peak results correspond to user-defined confidence level. And again, it can be parallelized and run in batch. You can get, and a key point too for a lot of people is this can output composite Ply stresses and failure metrics, which many random solvers and maybe not any of the main commercial solvers can do. Let's take a step back. We'll talk a little bit about vibration and random theory in general as we work through this here. But if we look at the types of vibration for sine vibe, and this is just one of kind of a few charts, ways you could break it down. So you think of sine vibe, it's deterministic. You know where the amplitude is at any given time. It's repeating and it's harmonic. So there's a single sinusoidal function. And then random vibration, it's random. You don't know the amplitude at any given time, but it is stationary. So the mean and standard deviation are independent of time. It's ergodic. So, and basically that just means the probability information from a single sample, it's going to be the same. If you take a sample at, this 10 seconds or 1 minute and a sample at this 1 minute, the probability information is going to be the same. So it's independent of the time you take the sample. And again, it's the form of it's a probability distribution that's Gaussian. And then if we look a little further here, and look at the random theory. So how does this, so you've got your random, you've got multiple time samples here. And what does it mean when we're talking about the probability function? Well, you've got your time history, and the Gaussian probability is just saying that, within this band, about 68.3% of your time history is going to be within this band. My apologies, that's actually 1 sigma, and 2 sigma, and 3 sigma. And then 95.4% is going to be within a 2 sigma band here. And then 99.7% of the time history is going to be within 3 sigma. And 3 sigma being often the standard for what we analyze too. And so your RMS value is going to be the 1 sigma value, and your peak value, your peak stress that you use to determine if your component yields or fails, is going to often be 3 sigma, 3 times that RMS. And there we go here. Now, the problem with random is that some of the results you want are not Gaussian responses. They don't follow a zero mean Gaussian distribution. Things like von Mises stress, it's always positive, and things like composite failure metrics. So they're not going to be zero. They're not going to be a mean of 0, and they're not necessarily going to be a Gaussian distribution. So how do you figure out what those peak stresses are? Well, traditional tools, they just calculate the RMS, and often you just multiply by 3 still. But that doesn't always apply to these. And so what we do is we actually have an advanced stress algorithm that determines the actual distribution of these non-Gaussian responses. So the von Mises stresses, the composite failure metrics, and we calculate them directly and can tell you what the peak is. And in an example like this, for instance, where you have the RMS, so you just multiply by 3. But when we run our processor, which we have extensively checked also with Monte Carlo simulations to guarantee the accuracy, in this instance, there's a 20% error. So if you had just multiplied by 3, your design is over-designed. Now, we've also seen cases where, especially in some of the composites, the actual peak is actually higher than the 3 RMS. So your design would be unconservative, which is probably the worst side that you could be on there. So we have the accurate results, and we can do them more accurately. And then just to hit again on the speed, this is an example again. It's that same example I showed previously, and just comparing to solution 111 in Nastran. If you're just trying to do accelerations, pull those out, SA Toolkit's about 3,000 times faster. I know these are like huge numbers, but I'm just trying to be accurate. If you're just trying to pull the stresses, 11,000 times, I mean, at this point, these numbers don't even matter. It's obviously faster. And then for things like, margin safety, failure indices, laminate strength ratios, you can't even get those results out of a solution 111. So it's not even applicable. But you can see, again, just think of what that can do if you could do random vibration analysis in seconds versus hours, minutes, days. Another thing that we like to point out, so going back to accuracy, you don't have to choose the random excitation frequencies. If you're familiar with Nastran or many other random solvers, you actually have to tell it where you want to calculate those, and you have to pick those frequencies. But you can see that you define, if you put too many frequencies in, it's going to cause the analysis to run a lot slower. If you have too few frequencies, you can run into errors. And even the way you distribute those frequencies, you can see here this red line, the PSD has way more frequencies included where they did the calculation, but because they didn't line up appropriately with the natural frequencies, the blue line with less is actually more accurate, and there's a 16% difference. So with SA Toolkit, you don't have to worry about this. It takes care of this for you. It does it accurately. You don't have to wonder if you're doing it right. You don't have to slow down your performance by putting in too many to hope you get it right. It's all done for you. Now let's go back to a question real quick. And before we get to a demo, I want to ask what software you use for random vibration analysis. Curious to see what the mix of the group here is today. Seeing quite a few others, which is good. I want to see if we were primarily a Nastran-based crowd or if we were using other things as well today. I guess there could be, the way I wrote the questions, it could be people using Nastran with other pre-post processors as well. All right, I'll close the poll, share those results, and let you see. There's a good, split between FEMAP and SimCenter 3D. There's a good chunk of people that are using the 3D response dynamics, which is good. That actually has SATK built in, so you're already taking advantage of a lot of the speed. And then the others. Unfortunately, I didn't have more questions. I would have liked to see, break that down even further and see what everyone's using. But let's go ahead and hide that. Now let's go to a demo. So we talked about this. let's go and pull up my model here. So I'm going to do this in SimCenter 3D today. Again, SA Toolkit works with FEMAP as well. You can actually dock it. It'll dock in as one of the windows there if you want. But I have a model here. This is just a generic antenna we built for demos. It has some composite materials here. And then we have like an aluminum horn. We've got some titanium brackets and such. And if you see them a little bit here, I should have colored them differently for you. You can see some 1D elements that are holding the horn and the secondary piece there. So I already ran a solution 103, that's the normal modes in Nastran. And you can see I've got the, just have the basic modal response here. And what we're going to do is go ahead and open up this is what the SA Toolkit looks like. And I'll just kind of briefly walk you through the random and show you some of the results. And show you how simple it can be. So we're just going to open the file. We're opening the solution 103 OP2. I already solved a sign in there. So that's going to read in that OP2. That's the results file. Now I created groups in here. I created groups of these different elements, and that's important because then when I have in here, I can read those groups in and actually get results based on those groups. So I'm going to read the Nastran input file there. And now it's read in my groups. So here's where we can just go and look at all the different tools and processes that we can run. It's going to be grayed out if you didn't have the model set up to use that processor. So you need to have the correct, if you want to run stresses, you got to ask for these stress results and so on and so forth. But I really want to demonstrate the random and just show you how easy this is. We'll just set up a random solve here. So I'll put in a base acceleration, and I'll just go ahead and import. I created one down here, just a random input profile. You can see that, just something generic I created. And we'll want to put in the scale factor. Like Nastran, it doesn't take into account units, so you need to just put in the appropriate scale factor for what you want your units of acceleration to be in. This model happens to be in millimeters per second squared. So that's in the X direction. I'll hit apply, and you see we've got one load case. If I were to go ahead and just create a secondary, I can actually initialize it from the previous one, apply. I'll create a Z direction as well. We'll initialize it and apply. One thing to point out that I didn't mention, in each of these load cases, you can do excitations in all three directions. So you can actually do, if you have a multiple input, multiple output MIMO type shaker table, where you can shake it in 2 or 3 directions at a time, this can actually solve that. We'll click OK, we've applied that. Frequencies, we're using all the modes. This will just check to use the, I did solve the modes with ResVec, so we'll include that. Modal damping, standard 2% damping, won't bother with that. And then here's where you can set your confidence level. And generally, especially for space applications, you're usually using 3. Now this, again, this doesn't multiply the numbers by 3. If you choose this, it's just doing it to the appropriate confidence level. And it actually, for von Mises stress and the failure metrics, it's going to figure out the appropriate peak value for you. Hit OK there. Now I'll create a stress case. Let's say I want to look at stresses on that aluminum horn in there. So I'll choose that group. You can see I had all my groups there. And I'll choose, if I remember what the results were and what the yield was in KPA. I think that's right. Put a safety factor in there. We'll hit OK. Hit OK. So you can create stress cases for any of the components that you want. I'll just do one. Now we're going to come in. So if you create a stress case, you'll want a margin safety table. So I can put it to, and this shows where you can export the results. I can do it in binary. I could do it in text, I could do it in Excel, use corner results. I do this, that's going to take the stress case that I developed there and put it into the results file. I want to look at accelerations. You can look at positive crossings. You can look at a scalar, again, for your translational. If you wanted to scale those. And this one, I'll just do all for this. I'll do all the accelerations. We'll put those in binary so that we can read that into SimCenter and look at the results. And then again, I'm going to do it, but I'm going to do for PSD because I want to see some plots as well. So I'll do that. And now I could, this is fast enough. I could run plots for all the nodes. I think there's a limit of 5,000, but I could run it for all of them if I want. But I just picked certain Excels. I don't want to see a plot for every single one. And we'll set that there. And let's say we want to look at displacements. Again, we'll just put that in here. I'll run that for all of them. And we'll click OK there. We'll look at the results and we'll show how this runs. So once I've set up that, it creates an input file, and I'll go ahead and hit start. We'll watch. This will take, I think this one takes 5 to 14 seconds. Asks for quite a few plots. Oh, you know what? Let me step back because this is so fast. I can show you this. I actually forgot to include the composite failure metrics. Let's just go ahead and rerun it. We already ran it, but I forgot it. We'll go ahead and rerun it. Let's look at the failure metrics for that front dish. That's one of the composite components in there. So you guys get to see how fast this runs twice. And click OK again. It's just overriding the input file. And we'll hit start. We'll run that again. Might take a couple seconds longer than it did previously. All right, you can see it's computing the failures there. And there it's done. So we'll click OK. We'll go back to the model so we can look at some of that. Well, let me take one. Yeah, let's look at it here first. So I'll just need to create a solution to put that in, put those results in. This could just be a dummy solution here. It doesn't matter. And then I will load in the results. I'll specify that. This is where you're going to pick your random OP2, because again, SATK works with the OP2 and then it outputs an OP2 that can be read into here. Do that. And then in addition, because there's some results, you want to add this companion file. There's this second results file because of how SimCenter reads in the data. We'll add that. And then we can go look and see our results here. Now I did, if you remember, I did XYZ load cases. So you've got 3 load cases. Here's your root mean square stresses. Now this is actually peak stresses. It's a naming thing in SimCenter, but these are your peak stresses. And I only asked for the peak stresses to be plotted on this aluminum horn, but you can see here that's plotted that there. And you can also see I have ply failure indices for that front panel that I plotted as well. And then if I look down here, we have our displacements. So you can look at your displacements. I plotted those for everything, or chose to get those for everything. And you can look at your accelerations as well, which are also for all the nodes in the model. And it's pretty simple. I'll go and show you now how we can do the, excuse me. I'll do a new one here. Oh, sorry. I'll open the, this is the random again, and you can look at your plots in here. So if we go ahead and create a new plot window, you can see that. Now let's go ahead and turn that to log. And you can also, if I go there and then I just need to make this so I can see what I'm looking at. If you could plot these together, so you can see there I've plotted my base excitation input and one of the responses at one of the nodes. So you can group all these together. You can create any type of plot you want. The SimCenter has a lot of great tools for doing that, and FEMAP as well. I want to just talk about some of the other outputs that you get from this as well. So we asked for some graphical plots. So if I click this HTML, it'll spit out plots like this automatically for you. So you don't, if you want to do a quick check, you can just come in here and check these. You don't even have to plot them in SimCenter first. This can also be a good check if you want to just make sure, okay, was my RMS value on my input correct? Did I actually solve it correctly? And you can go through and look at these. And I already ran a sine. I didn't want to spend too much time going over the sine analysis for you, but I ran the same thing for the sine in there as well. These are all your plots you have. So you can see the sine responses that I had there. Does the same thing for those. And then just to really briefly show you what we have from the modal and the energy processors. So if we're looking at results from the modal, you can plot the effective mass, the bar chart, sort of a cumulative effective mass plot, and then get the data summary. You can highlight it based on percentage and the energy processor as well. You can get, I kind of like these. I mean, it's a cool looking plot, and can be useful to kind of quickly determine, okay, based on my groups that I had in there, which one of these modes are activating which group. It's just a really quick visual to run. And that's the demo. That shows you, I mean, we had a model. The solution 103, the normal modes, took on this model about 3 minutes to solve, just over 3 minutes. And you can see we had random results in, I think it was 12, 14 seconds, just a little bit depending upon the results you pick. So if we go back to here, just to close, Assay Toolkit, I mean, it's a best-in-class tool for simulation of base-driven random and sign-bind analysis. If you're doing any design that requires random and sign, if you're doing any sort of random and sign testing that you need to do analysis for, this tool is going to do it faster than anything else. And it's accurate. We saw, and I tried to spend a good bit of time to talk through how it's accurate, especially for those non-Gaussian responses like the von Mises stresses, and the fact that it can actually do your laminate ply failure metrics, which the other main solvers can't do at all. Now, I just want to add one last question, and then we'll go to questions here. I want to see if, you know, how would you prefer to learn more about Assay Toolkit? I'm just asking this because we're interested in what you guys are looking forward to. We do webinars, we do road shows, we do online content, and just want to hear what people are interested in and what you'd like to see. And I'll also just say that if any of this is you know, please reach out to us if you have any questions. I'll show some links on the next page where you can learn more. And if you are interested, we are allowing people to have a demo license of Assay Toolkit. It's free. We'll set you up. You can try it out. You can use it and really see how it works within your workflow and see if it works for you. I'm pretty confident you're going to find it's fast, it's efficient, and it really makes things easy. See, I'll close the poll here. A lot of people like the self-guided. I'm that way too. I don't like asking a lot of questions up front. For people who are interested in, you know, training and software evaluations, one-on-one meetings, please feel free to reach out to us. we're more than happy to do that. Local in-person workshops as well. Like I said, we do a little bit of everything. We provide people with software. We help set up and implement that software and those solutions for you. We'll do the training to get you started. And then for my group, the simulation services, if there's something you don't want to buy the software, if you need somebody to augment your staff, we're more than happy to help out. If you need any structural, thermal, or CFD simulation services as well. This random vibe, and many other areas we're experts in, and do a lot of the actual programming of these tools ourselves, and we use them ourselves. That being said, let's see if there are any questions. We've got about 19 minutes here. Let's see. Oh, I forgot to share the results in that last poll. Sorry. I thought I clicked share. There's the results for you. So yeah, the QR codes there's a link to just my LinkedIn there if you want, but also feel free to reach out to me there if you have any questions. Also the QR code on the right, that'll take you to our page on our website for SATK, where you can get some more info, download a brochure. In addition, we'll send you out a white paper that goes into some more of the details of how this solver works, and allow you to reach out to us that way as well.